Okay. Go ahead.
Hello. We are Hyperxite. My name is Jason Lee. I'm the chief engineer.
My name is Adora Fadris. I'm the project manager.
And I'm Daniela. I'm the assistant project manager.
So what is a Hyperloop and why should we care? Basically, it was proposed by Elon Musk in 2013 in his Hyperloop Alpha white paper. It's basically a new way of transportation that's more sustainable and more efficient, and could basically be the fifth mode of transportation that we use in our everyday lives. It's designed to go at really high speeds in a vacuum tube. So basically, it should be able to get you from Los Angeles to San Francisco in 30 minutes, which means that you could live in Los Angeles and work in San Francisco, which is a pretty big deal. Next slide, please. So a bit about Hyperxite specifically. We've been to the past 3 Hyperloop pod competitions at SpaceX, and we're planning on attending the 4th one. That's our plan. So we've been able to make it to the finalists of the past 3 competitions and the first design weekend that was hosted. So hopefully this competition, we're planning to exceed expectations. Yeah. So our goal for this year is to build a high-speed self-propelled pod and complete a safe and successful vacuum run at the 4th SpaceX Hyperloop pod competition. Our top speed is 245 miles per hour, and then we have some other safety requirements like being vacuum safe, monitoring our pod at all times, and braking within a safe braking distance. Seems pretty reasonable. So this is a diagram of our pod trajectory. As you can see, most of the time is just spent accelerating to our top speed of 245 miles per hour. We don't have a coasting period, so as soon as we reach our top speed, we just begin braking and hopefully brake safely within 100 feet before the end of the tube. So for those of you that were here for our fall peer review presentation, some of our specifications have changed. For your reference, that is a scale diagram of what our pod will look like in the Hyperloop tube, which is where we run. So top speed, 245 miles per hour, as I previously mentioned, and which is 120% faster than our previous design, which was last year, not just fall quarter. Also, our pod is now a little bit heavier than what we anticipated in fall quarter. It's now at 180 kilograms, which is still 30% lighter than our design of last year. So I'm going to give you kind of a rundown of where all the subsystems are located on our pod, and then we'll continue to go into detail of each subsystem. So the front of the pod is actually on the other side, outside. So we have our vertical stabilization wheels, and then as you move further back, we have our electronics system and our pressure vessels on the side, and then we have our coolant reservoir, which cools our motor over here, which has a pointer. Thank you. Which one? The one labeled laser, cool. So that one is our low voltage electronics, as well as our sensors and PCB and all of that fun stuff. Here we have our coolant, which supplies coolant to our motor because it gets pretty hot during our run. This is our motor controller. It's supplied by our high voltage system located here and here, and the pressure vessels. And then we have our braking located at the back, as well as our pneumatic system and our the rest of our damping or stabilization. So about our chassis, a major accomplishment for this quarter was that we were able to secure a sponsor for our chassis. It's made entirely out of carbon fiber. The sponsor has also helped us through the design and making sure that it's manufacturable and will not fail and is dependable and all of that fun stuff. And we're also in the to-do, we still need to complete a more in-depth simulation. Since carbon fiber is a composite material, it's pretty tricky to simulate, so we're still working on that. So our fairing is the part that covers the whole pod. It is designed to reduce drag, and the question we always get is, why do you need to reduce drag if you're running in vacuum? That's because we're not running at 100% vacuum. We're actually at a pressure of 7 torr. Yes, 7 torr. So we do need to consider drag at those high speeds. Another major accomplishment is that we did secure a sponsor to help us manufacture this fairing. This and the structure were one of our biggest costs, so it's a major accomplishment we were able to secure this sponsor. And also we need to run simulations because of the same issue with the structure of it being a composite material.
So this is our stabilization system. We have lateral, vertical, and underside wheels. So we were able to complete all of our final designs as well as run analysis on those designs. We have a minimum factor of safety requirement of 2, and all of these designs met that requirement. Right now we're completing a tolerance analysis and completing our drawings and purchasing the coilovers that we intend to use. Later down the line we'll be manufacturing the components, assembling them, and testing them. So for our power systems, we have completed our power system layout, as well as deciding to go with pressure vessels to put our batteries into, since they are not vacuum safe. Right now we are testing the batteries, discharging them, taking in temperature data, and we're also speccing high-powered feed-throughs. Since we do have 2 separate pressure vessels with batteries in each of them, they do have to be connected somehow. And after that's completed, we'll be completing the PCB design for our pod. For our controls, we previously said that we were going to use the BeagleBone Black, but we decided, just due to time constraints, that we're going to be using the Compact Rio again, as we did in previous years. We are currently trying to use this to troubleshoot our motor, to do some motor testing, and we are also using similar code from the last year's pod, but we're revamping it for our new pod that we're making right now. We also need to run tests and calibrate our sensors, as well as complete that finalized software that we're going to be using at SpaceX's competition in the middle of summer. So for our braking system, some of you may know we are using a magnetic braking system, which uses a Hallback array, which basically contains all of the magnetic field onto one side, and that side being in here. So there isn't very large magnetic field on the outside, so it's not very dangerous if you get too close. If you get too close. Sorry. And we also ran analyses on those on that braking structure as well. Right now we're trying to purchase the off-the-shelf components we need, such as the actuators in the middle here, and we're also looking into trying to make them engage a little bit faster. The restriction there is the outlet of our pneumatic system, which we'll be getting to later. Depending on the size of the outlet, it's going to restrict how much air is going to escape and how fast that air is going to escape. For our propulsion system, we updated the propulsion assembly right over here. We also ran some preliminary analyses for that structure with some dynamic loads. We are also finalizing this in the next couple of weeks so that we can continue running those dynamic load cases as well. This is our trajectory, showing that with these different weights, we can reach a 250, 245 mark, and then decelerate down to 0. We're also in the means of writing up a testing procedure for testing our motor at low speeds. Obviously we don't have enough space to do a full 245 mile per hour test, so we're going to do very small, short tests just to make sure that the functionality of the pod and the logic in the code works.
Our cooling system will be used to cool our motor and our motor controller, and we'll be using deionized water stored in a half-gallon reservoir. And this past quarter, we were able to resize our tank, because last quarter it was approximately 0.85 gallons, but we were able to make it smaller this quarter and do 0.5 gallons. And we're currently waiting on our components to arrive to begin assembling. And in the near future, we'll be completing part orders for manufacturing as well, and contacting vendors for silicon coolant tubing. Our pneumatic system will be used to actuate our braking subsystem safely and effectively, and we recently just redesigned our pneumatic system. That's the new schematic shown here to the right. And we're currently speccing out additional solenoids, relief valves, and pressure regulators at the moment. And in the near future, we'll also begin just waiting for our components to begin manufacturing and assembling our pneumatic system, as well as writing procedures to just test our system. So this is our team organization. Right here in this branch, we have management, which includes myself, Jason, Adora, and our operations manager. This technical branch right here includes our subsystem leads and their respective general numbers. And this non-technical branch right here includes documentation, log management, and safety and outreach. And this team organization directly corresponds to our work breakdown schedule. And this shows how major tasks to complete our pod are organized within each subsystem and how they all interconnect to complete our final pod assembly. So in the red, we have braking right here. The purple is piping and cooling. The green is dynamic systems. Blue is static structures, and orange is electronics. And these all contribute to our final pod assembly right here. This is our project timeline. We're currently beginning manufacturing and assembly and starting component tests, which will carry on into spring quarter. In the spring quarter, we will begin our SpaceX safety package and begin full systems testing. And that will carry on into the summer until competition, and our competition date has yet to be announced, but we're anticipating it to be around July or August. For our budget, our total pod cost is $97,831. Fortunately, around 27% of that has been covered by donations from our last team. Although we've been fortunate enough to have generous in-kind sponsorships, we do have $8,000 still unsecured, but we're currently working on closing that gap and contacting companies for sponsorships and seeing what we can do to reduce that number so that we will be fully funded. And this pie chart just shows how our pod cost is broken down by subsystems, and this just shows our full funding plan right here. Any questions?